thanks everybody for coming out. So today, in this presentation, like Vince called me last week, he's like, hey, can you present your DevNexus presentation next week? I'm like, well, I haven't even started on it, but I'll see what I get done over the weekend. So I managed to put together there's about 70 or 80 slides. The final version will be available in a month, but I think there's a lot here, and I'll try and stress the common themes. This is less about code and more about a data lake and a fast data platform. Obviously, everybody talks about data lake, big data, but what are you really getting yourself into technically? What are the challenges that people engineer themselves into, and the hurdles to overcome and that kind of thing? And then what are some of the newer technologies, obviously, that can realize more and monetize more of the value from a real-time data stream versus the old batch pull models. So again, yeah, so this is a sneak peek, and for those who don't know the difference grammatically between peak with an A and an E, that's, I found that funny. It was a little late last night, so forgive my attempt at humor. Some of my contact information, obviously, my email and all that kind of stuff. This presentation's up on SlideShare as well. So I try to make sure I include all the links for everything I reference. Usually that's where all the good code is, so I don't bother cutting and pasting something somebody else has put together, although I may have a little demo in a month that kind of pulls all this stuff together. It's about me. I'm a senior solutions architect at Cox Automotive, and for those who don't know, Cox Automotive owns about 40 different companies: Kelley Blue Book, Dealertrack, Auto Trader, Manheim, just on and on. VIN Solutions, pretty much everything in the supply chain of a car you can imagine. So it's a $19 billion global company. I'm in a strategic data services group, which is horizontal sliver. So we're attempting to consolidate some of the information from different business units together. Historically it's been a Hadoop platform, but now we're branching out, going into Amazon more often, trying to build cloud native solutions, which I've done elsewhere. And then just some other things about me. I'm pretty bad at the bass. I'm not allowed to play at home anymore. Some previous presentations, I gave a few talks about Docker a couple of years ago, when everybody laughed at me when I said it'd be the thing everybody uses, and now it's kind of the standard now. So, but it's kind of cool when considered with microservices and all the other different techniques and styles for building software. Everything's starting to converge into to kind of build upon each other. So here we have the agenda. So just a couple brief categories. I'm going to give a really brief history about some of these things, go into some background about reactive programming and architectures without reinventing the wheel. I'm sure a lot of people have already read on this stuff, or are already experts on it, or already actually using this at work. So I'm trying to tell a story in context of reactive principles and some of the technologies that are mentioned, but also a data lake. And then when you're talking a huge enterprise, what kind of problems do you run into? How do you make it work? How do you scale organizations? How do you even staff it? That kind of stuff. So Ford, just a quote by Confucius there, that there's nothing wrong with failing. That's at the Reactive Summit in Austin. There's a great talk, and one of the presenters stressed that it's important to have room to fail. You need time and room to fail, and usually you only have time and room to fail in academia, but companies that succeed or innovate well usually find ways to fold that in. So why is reactive important? That will be one of the themes I'll sprinkle my opinions or perspective in on the slides. It's important that obviously everybody knows reactive systems and programming doesn't mean reactive management. So sometimes there's an impedance between the ideal architecture or a good architecture and the way a business is run, which may be because of budgeting or accounting, zero-based accounting. You got to plan a year ahead, so you're always behind technically, and by the time you plan for that, you're behind again. So, how do you manage that cycle? I believe reactive underpins everything, pretty much, in software. And most of the concepts aren't new. They've been around for 30 or 40 years. It's just different technologies, and people, as you work on more things or exposed to more technology, you see the same types of common patterns. Larger companies, it's probably true for, have a tendency to go for COT solutions, or they'll go to a conference and they'll see something that looks cool. Hey, how do we fit this into our business, instead of understanding modern ways of building software and evaluating from a more structured, logical perspective, what tools satisfy what I want to do versus how do I fit this tool into the enterprise. Then also the importance of governance, tenancy, entitlement, security, just as bedrock principles, like how in a data lake, which by nature is completely unstructured and free-for-all, where people are just literally dumping information, and there aren't many good tools for keeping track of what's in there, the structure, the entitlement, all that kind of stuff. How can that be rolled into it without making the system unusable? On the other side of the coin, if you make the system usable, then you can never have governance because people can bypass it. So I'll talk about a few ideas around that. So the use case I'm approaching this from is building a system that can scale to millions of concurrent processes and billions of events. So that rolls out quite a few technologies, and there's only a couple really. Erlang, obviously, because it's been doing it for decades, and a couple other actor-based systems. Obviously Akka is one of them. That's been proven. So we're talking about real-time data, for application components, but also, analytics and middleware, because companies aren't just software developers building applications or end users using applications. They'll have oftentimes large data science departments that are mining the data. And those people have a particular skill set. They're using certain tools, and they don't really care about everything. If their job's difficult, they're not going to be happy, and then that's how things move along. So it's really just a journey of successive refinement, innovation. Anyway, enough about that. So the briefest history of this, and this is literally a one-pager, and I tried to add a little ominous tone to the quotes because there's a message that underpins all this. Is, reactive isn't new. It doesn't mean it's bad, but I think people have kind of ignored it or not even known it's there or realized its value. Principles go back 50 years. We'll talk about that more in a little bit. Obviously, Erlang was one of the main two. The other one was another white paper that's well known. The bedrock's messaging, just passing messages around and having simple components and building the platform so the components can operate in a highly available way. So jumping into reactive systems, patterns, and implementations, and I'm borrowing from a lot of light pen collateral because that's time to do over the weekend here. But since they're kind of the inventors of this, they're a really good voice, and they have very good collateral. So I'm not ashamed of it. The Reactive Manifesto, I'm sure many of you have signed this. I know quite a few of you have. Many organizations are independently building software to new and similar patterns, and many don't even realize that. So there's been this natural convergence to this implementation, architectural style, and then people started writing about it. People working on actor-based systems said, hey, wait a minute, there are bigger factors at play. How can we start to create a more unified, holistic view of all this? Whereas yesterday's architectures just don't cut it. They're fine, and they might work great at smaller companies, end-tiered architectures, client server, whatever. But at some scale, at some point, company just outgrows it, and at that point it becomes costly to replace. You could have customer impacts, on and on. When nowadays we have these modern architectures that you could use at tiny little companies or huge companies, and they just operate the same way, and they automatically scale out and up. So again, reactive is kind of the offspring of Akka and Erlang. Akka is the new flavor of it, and a good starting point is just the architecture design pattern. I have a slide that summarizes some of these. So basically, what is reactive? And without reading this, since everybody else can read faster and I can talk, It's just a set of design principles for creating cohesive, simple systems. And it's a way of thinking about distributed environments, distributed systems, a way that allows multiple services to act as a cohesive whole, and you can orchestrate them, and you get the benefits of resiliency and high availability and all that kind of stuff. Components may qualify as reactive, but when combined, that does not guarantee a reactive system. So that may sound contradictory, but it'll become clear in a moment. So reactive begets, there's three classes of information or context that people probably naturally think of when you hear the term reactive. There's reactive systems, which is the architecture of the whole, how the system works, that of reactive components. There's reactive programming, which is declarative event-based thing, how you actually code the components, how they actually work in context of the platform. And then there's the probably misapplied term functional reactive programming, and this is one thing the Lightbend people are very big on. Jonas claims that there's a very narrow and strict definition of what FRP is, and most of these new frameworks actually aren't functionally reactive programming. They're reactive programming models, more so than functional, but I think that's splitting hairs. Reactive is a subset of async, obviously, because the cornerstone is async and non-blocking. New information drives logic versus control flow-driven thread of execution. Messages go in, actors wake up, and do some stuff, maybe change or pass the message around, that kind of stuff. They don't block. That's one of the ways that we ensure that it's scalable. There's a couple different classes of reactive API libraries. They're either declarative, functional composition or combinators, that kind of stuff, or callback based, which is, we've seen for longer with things like Spring or these iPaaS frameworks where you register callback hooks, and it's a way of integrating different apps. Now oftentimes they'll have stream-based operators, simple windowing triggers, whatever. Features have been in something like an Esper and EDA engine for 10 years or longer. The interesting distinction between the two is that reactive programming is event-driven, and reactive systems are message-driven. And the difference is actually pretty important, but most of the systems kind of bridge the gap. They do messages containing events, but the events themselves are a byproduct of state machines within components, and you may react to those or have handlers, but then the actual communication between systems, part of which in turn makes them highly available and resilient, is message driven. So the actual state or information that's sent around is the event. So getting into that in a little bit more detail, there's this concept of data flow programming where we emphasize flow of control versus flow of data. And examples of that would be futures or promises or reactive streams, where we have unbounded async, non-blocking back-pressured pipelines, data flow variables, single assignment variables, cell in Excel, where if you change it, that change may propagate downward. So all of those are reactive concepts, but it's in the concept from the perspective of a data flow. So technologies that do this include Akka streaming, RxJava, Vertex, that kind of stuff. So it's basically workflow-ish composing activities. From the reactive stream specification, it says that it's a standard of interoperability between different reactive programming libraries, including the JVM. So, Akka streams follows the standard. Java streamings and JDK 9, the flows model, will follow this. They should all be able to interoperate as long as they adhere to the standard. But it's just an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure built in. So rather than forcing a developer every time he writes a service to handle back pressure, and usually sometimes in the past they only did that when they got a bug. Hey, your service fell over because the queue fell up. Well, I need to write a way to handle that. Do I push the error back onto the client, or do I have the server handle it? What does that mean? Why do reactive programming? So why don't we just keep coding the way we've been coding, using the same frameworks we've been using? I mean, you can. There's nothing wrong with it. Depends on the company, but some of the benefits are, improved utilization of compute resources, more efficient use of your commodity hardware, more efficient scaling, more efficient operations, lower cost of ownership and management, that kind of stuff. You'll see an increased performance reduction because serialization reduction, efficient application of like a Cairo library or something like that. Because all this information is going over the wire in a clustered environment. So then there's Amdahl's law at play. There's Gunther's universal scalability law, which deals with concurrent distributed systems and the cost of coherency. And the full explanation probably has been worth discussing because it's easier to go to the wiki and read it. But and most of us have already read on that. Productivity, reactive libraries are very simple, fluent DSLs. You get to use Scala more often than Java, so you're writing a lot less boilerplate code. And you're not limited to those two either. You can use Python or whatever you want. And in the future, I imagine pretty much everything will be on this kind of a programming model. And the coordination between components, I/O, flow control, that kind of stuff, the frameworks will handle that instead of having to deal with it programmatically. And it's great for composing components that become workflows, that you need to be back pressured, scalable, and high performance. So really what I've described there is what Akka does. So we have concepts of event-driven and message-driven. So looking at this a little bit more closely, event-driven, you have data flow chains. Message-driven, it's the basis for a reactive system. It's how the messages are passed. You want the messages to be highly available. You don't want the messages to get lost. The events we don't necessarily care as much about because those are internal states of the components. Those reactive components, when they fail, they would highly available. Another actor would pick up that state, the message, and be able to reentrantly reprocess the information. So events are basically facts that can be observed at a point in time. And in a reactive system, a message-driven component, it's long-lived, it's addressable. Focus on resilience and elasticity via the communication, which means just the high availability of the messages that are flowing around with supervisors. It's also worth noting that events aren't necessarily directed, they're just facts, whereas messages are directed. They're sent to another component to be processed or to trigger some kind of activities. So it has a clear destination and addressable recipient. To quickly go through some of this. So this makes it a little more concrete. So event-driven and message-driven. Events within messages, that's what most people are doing today. Unless you have an advanced CQRS system that's actually managing events separately. Good examples at AWS Lambda functions, like somebody creating an SNS topic and then sending it to SQS and attaching a Lambda function on and hoping that Lambda function spins up within the 5-minute contract if it's been passivated. Distributed streaming systems, which a lot of people have used these, and that goes all the way back to 2002 in message-driven beans. It's kind of the same kind of concept. It just more of the plumbing and the scalability and the clustering comes in behind the scenes. So you can do this with Flink or Kafka or Akka streams or Spark streaming, or there's so many different streaming technologies, but there's actually subtle differences in terms of the use cases for how we want to use them. So the pros of this model: abstraction and simplicity. But we have cons when we combine events and messages together. We lose some control. Messaging forces developers to deal with the complex realities of distributed programming, whereas if we could cleanly separate the two, they wouldn't necessarily need to care. Things like failure detection, message delivery contracts, duping, consistency guarantees, and probably a good example of this is, you can't hide behind a leaky, bad abstraction anymore that pretends the network doesn't exist, like XA or RPC, because we all know that if we've coded in those, that you have to code for exceptions or failures in the distributed environment, and really we shouldn't have to do that. So this is from the architecture in like Ben, so in the Reactive manifesto, but it basically explains, what are the tenets or characteristics of a reactive system. They're responsive, so obviously low latency, that's important. Consistent, predictable performance. Usable, it's essential for utility. If something isn't responsive, you can't really use it. It's not, you have happier customers, and it'll expose problems quickly, so you can fast fail. Resilient, that's resilient through failure, through high availability, replication, those actors across nodes and the state management and the supervisors. Failure is isolated to components, the concept of bulkheading, which we'll get into a little bit later. But we can delegate recovery to external components in an actor-based model, like a supervisors. You can have actors watching other actors and taking care of each other, and if something happens, it's on another node, it can fail over. So you can have lossless and different contracts of guarantees. And the client doesn't have to handle the failure, so it's not the old days where you give somebody a REST client and then they'll have to code all their services for failure, and this thing could blow up that I'm calling, when really it should be more graceful than that. Elastic, that's just about scale. So you could have a small company with 1, 2, 3 nodes running an actor-based system, and suddenly it gets busy. If you're using Mesosphere or whatever, you can automatically scale out horizontally, spin up more nodes, and the actors start going out that way. It's devoid of bottlenecks or hotspots. The framework will take care of that, especially if it's Mesos managed. And the important thing is that performance metrics drive the predictive or reactive automatic scaling models. So that will intelligently scale. You won't have an admin going in and saying, we need to add 10 nodes, it's busy. It just autonomically happens. And then fourthly, message-driven, asynchronous, non-blocking, and based on the concept of message passing. So some common patterns. Most of these have seen some versions of these. The one that was new to me recently was Saga, the way that's used, which is kind of interesting. So the single component, that's very similar to the microservice tenets. Component does one thing. The whole SRP concepts, I'm not going to go over that. Let it crash, which is big. Design for failure is a common hot topic now. Most of the better developers have been doing this for a long time. If you're following test-driven development, that's part of how you code. The failure is a part of it, but the framework that handles it, the framework's been designed in a way such that it assumes all your components can fail, and that it will offer features to gracefully recover from that. And then some of the implementation patterns are more than this, but circuit breaker and Saga. So circuit breaker obviously is just a way, if there's a failure, it's a way of breaking the communication chain, whether it's pulling a node out of a load balance pool, or an actor being isolated by the supervisors or the load balancer actor, so that it can have time to recover, and it might have to reconstitute stuff. That's one of the patterns, is that components can be destroyed and recreated. That's the preferred model versus having a component try to recover or fix itself through complex error handling. And it's actually a concept from electrical engineering as well, so conceptually they're very intended to be similar. Saga is divide long-lived distributed transactions into quick local ones. That's really parallelizing, with the goal to have forward and backward replay recoverability, which means that you have to have a bunch of save points to save state. Then you can roll forward and backward, that kind of thing. But the state model of an actor system, depending on the type of failure, may use this pattern to help recover from certain types of failures. Yeah, it sounds complicated. Definitely some learning needs to occur. But I think we all know we're always reading. Technology is always changing. If you stand still a year from now, there'll be something that is important that we all need to know. And if somebody else knows it and you don't, you're not in a very good position. I'm not going to be able to build reactive systems with certifications. So, a big company, I run into a lot of Amazon certifications, which are great, but what's actually been built? So I look at more, experience, what people are doing, how they're connecting the dots, how they think, how they learn, that kind of stuff. Certifications are great. That's doing your homework. You can also read a book at the same time. So the new is based on evolution. So I think from what I've been discussing previously, a lot of these are old concepts just assembled in new ways, but there really isn't anything different here. Some of the technology is new, but the way it works isn't. And paradigms and patterns aren't isolated to components or technology necessarily, which is kind of the point of that. So here I'm just going to summarize the enterprise, some of the challenges of working in different size companies and how it relates to reactive programming now that we've had a summary of that. So now that's maybe a startup. It's definitely not a larger company. So we all work for one company, or if you're a consultant, more than one company. And the simplified, what the points I'm going to try and make is that each of the company has a size, a complexity, and an age. Startups, I think we all know the differences there. Less legacy overhead. You're building something new. You're building it from scratch. You get to pick your tech stack and own it at the end of the day. More than likely, you're going to get to use the latest and greatest cloud technologies. That'll attract a different type of resource. Some people call them unicorns or purple squirrels or whatever. But interesting environments to work with. Generally, you're trying to build up IP or to create a niche product and to derive value, and oftentimes to be acquired by somebody else. So they'll look at your architecture closely. So a lot of advantages there, but and there are also challenges. Mid-sized companies, that's where you start seeing some legacy overhead. May have a blend of new technologies. They're probably not buying that many enterprise packages like Splunk and all this kind of stuff off the shelf versus doing custom programming. So more strategic application there, and probably more cloud adoption. At least that's what Gartner says. Large companies, that's where it gets interesting, especially a company like Cox, where we have 40 different companies, and every one of those companies has its own dev staff. So we have a whole bunch of different ways of doing things. But it all needs to work together, and at some point, certain functions need to consolidate, or we need to be able to share resources. So, I think large companies probably where the term tech debt or culture debt comes from, because people are around long enough to create or make mistakes and other things, which is fine. Usually large, very complex environments, and that's not necessarily because of the weight of the systems, maybe how they've been built or the technologies that were available at the time, maybe some of the decisions that were made in the past. So, the point with this is that, the ability to adapt a reactive architecture, it's more of a challenge here. So how do you do it? Where are the traction points? Where can it be implemented to add value? No. More politics, which is, comes with the territory. And you'll probably find interesting blends of on-prem hybrid clouds. So these platforms that like a Terraform that abstract where you're deploying to, you'll probably see more of those really expensive tools so that you can work with legacy systems and develop with the more modern stuff. An enterprise, larger companies might have a stronger customer-facing or revenue-generating face, which is That's where the risk or the fear of adoption comes from. And I'm just sharing this because I've run in this at a couple of companies, and you try and sell a new idea or new technology, like these considerations invariably fall into play and a lot of other stuff. A lot of data movement in older applications when, more modern ways with federated query, trying to take advantage of that. Do you need to move the data from A to B, or can we engineer it so we have common platforms that allow us to share the information with less complexity, while also enabling the real-time enterprise. The old batch-oriented, hey, go pull my answer, go process my data from a data lake, may not always be practical. Eventually you reach a scale point where you can't query the data. You need to act on it in real time. And for certain types of systems like recommender systems, it makes sense to, if you want to monetize it fully, you need to act on data as it's created, which is the whole point of Reactive, and that's what it offers. So some of the other benefits of Reactive, save money, you can become more agile, working in components. The same actor system can run on a MacBook, or it could deploy it up to Amazon and spin up a 100-node Akka cluster if you wanted to. More powerful data processing. The older ETL packages, the Informaticas of the world, Pentaho, Talon, whatever, a lot of them doing EIP type functions. Akka streams can do that, and a few other technologies, or even Camel is a good example. If you want to do that in a clustered environment where the hardware will automatically scale to the load very efficiently, like the reactive systems are great at that. And perfect use case, like Erlang has been doing this for 40, 50 years. That's the software that runs in the telco switches. So probably trillions and trillions of events over the decades through those systems, and they don't go down. And obviously reactive components are more decoupled, so you have better interoperability, more composability. Can plug them into CI/CD systems in more interesting ways. You can even use your Jenkins to manage deployments of stuff or to run jobs. So like the need for like a job scheduler, control M, most people are just using it to run a shell script. Why not just use Jenkins for it or something else? Use easy tools. So it opens more options. And I think the most important point is, the autonomic automation. So autonomic is, self-healing, automation. The system's built so that it auto-corrects itself, which is kind of the concept Akka is built on. But again, you can't forget the other side of the business. All the technology is interesting, but ultimately you have business users who are non-technical, and larger companies have more non-technical people than technical people. And a company like Cox, we literally have thousands of SaaS users. We're just, all the different business units mining the data in their business unit, and they can't work across the companies because of the restrictions. But those people are working in SaaS and they may have been doing it for decades. So convincing them to use the reactive systems is more of a challenge. So especially from the perspective of a data lake. So that's where, and later on we'll discuss this, we need curated data sources and modern technologies that they can use. So they could jump to something in Amazon like a QuickSight or a Redshift or whatever, and maybe not use the CLI on their desktop anymore. If we have Databricks, they could use notebooks, that kind of thing, kind of like the iPySpark notebook approach. With Databricks, it's easier to automate it and to turn it into a product. So that's some of the friction that we run into. We have to keep this in mind. I found this slide. I think it just explains some of the volume on the internet and the volume of data that's created. I think this is about a year old. We're just like 2.5 exabytes every month created. And 90% of the world's data created within 2 years. So it's like, you look at your data lake, and like if you have a 100-node Hadoop cluster, and think about that for a minute, and we want to acquire all these other companies that maybe they're tracking every weblog or clickstream event, and then suddenly there's an analytical reason for capturing that at an even more granular level. Then we need ways to handle that from a technology perspective more efficiently, where a batch approach definitely won't work. So that's where these scalable reactive models with actors operating on the system and different types of streaming systems allow us to manage this type of data. But it's one thing to have a data lake and to create curated resources. We'll get into some of the challenges around that, which are the well-known drawbacks of a data lake, and kind of those are things that people need to be aware of when what they're getting into. So fast data. So this is all the rage right now. Concepts have been around for quite a while. Lambda architectures and all that kind of stuff, or distributed caching, several years at least. But good Stephen Wright quote to add some humor. But fast data is kind of the evolution of big data. Big data is just kind of like a sink. You have a constant stream of inbound data at incredible rates. The old way was to store it and then analyze it, run Hive or Pig jobs or whatever. Or hey, maybe I'll put Tez behind Hive, so you might think it runs faster, even though it's still really inefficient and complicated and breaks all the time. Or else they'll add Impala, which is some relational database, but again, that has its issues as well. Then some of the new innovation, to add these more real-time frameworks, adding Spark into Hadoop, yarn managed, to get better response time, and we'll talk about Spark a little bit later. But the point is, why not act on and analyze the data as it's received? Reactive models, the original promise of a message-driven bean, but it was really hard to use way back then because it was one broker, one server receiving it. Now we're talking millions of messages, so there might be hundreds of servers that need to work in parallel, and we can't share state across them. So we have technologies such as Akka, Kafka, Spark, Flink is an option in there as well. A whole bunch of other stuff too, so probably add about 20 in there. But I think the limiting use case would be, for a company that's going to be data intensive, millions of concurrent actors, billions, potentially billions of messages. It may not be saving billions. There could be some load shedding for aggregation purposes, whatever, but doing that in real time. And then the ability to forward this to destinations, a data lake or other destinations. So it'd be like a data distribution type framework. Found this slide. This is kind of interesting, but it kind of makes the point that big data is flooding that streaming. So you have state machines and IoT in there. But there's profit in the data if you can act on it faster in some cases. Some analysts don't care. They don't, if they get their information and it's up to date for the last week, big deal. And then concepts of blooming and machine learning and all that kind of stuff, and the graph features, which are popping up in about every technology. A couple years ago, there weren't that many graph engines available. Neo4j, and then Titan popped up, and now things like Cassandra are adding it, and Akka and Spark are going to be adding that. So the point is that fast data is just the way the industry is going. Many of the technologies we've been using for years, their features are just becoming part of, common components that have been around for a couple of years. The easy part is, building a system from scratch, using these technologies and architectures. Startups have it easy, I say that, but having worked in them, it's always that I don't think that's a fair statement, because you're probably working 16-hour days, doing 3 different jobs. And the ability of a company to adopt disruptive architecture is probably inversely related to its size, which means big companies move slower. It's just a real money where software costs money, and bigger the impact and more planning, more people involved, that kind of thing. So how to reconcile with legacy architectures implementations. So if you want to add reactive principles, these reactive technologies, adding in Kafka, easy, great. That's replace ActiveMQ, awesome. All kinds of broker complexity gone, and you get all these benefits. But then adding something like a Spark, if you already have a Hadoop there, People have probably been suffering the MapReduce pain for a few years, so that's easy. But then selling an Akka, where it sounds a little more complicated, it's a harder sell. So, finding a use case to show where it has value, kind of walking a company through that process is, I guess, part of the fun I enjoy anyway. So, we run into plenty of Frankenstein or stovepipe solutions, and usually through good intentions. That's that quote, "The road to hell is paved by good intentions." So, or a late night fix, or somebody cutting a corner, but they just may not have known better. Or maybe they used the technologies that were available. So enough of that, now for the fun stuff. That's just kind of setting the table for talking about Akka and Kafka and Spark. So because all this is in the context of data movement, the company is doing something with this data. And one of the most important pieces of the analytics side. So real-time data for applications and also analytics, so dual purpose. So the core techs I'll cover briefly are, Kafka, most of us know that already. Spark, many of us have used that. Akka, probably less frequently used, but the Akka HTTP as a replacement for Play is appealing to me, part of the Lightbend stack. Then Alpaca, because I've been a big fan of Camel for many years and what it does and the way it does it. And that's basically Camel in Akka streams, which is interesting. So this is their marketing slide, part of it. I didn't include the management piece where they use Mesos. So, and I won't talk about this as much. That's, you can use that for APIs, but you can have Akka HTTP up here, which means you don't really need this anymore. You can still use it. And then Kafka, there's a lot of features in Kafka Connect, but they don't talk about the schema registry, where you can have an Avro schema registry, which is pretty useful in a data lake for managing what the information looks like. Spark has a lot of interesting things. So the streaming model, or the batching data through it, doing machine learning through it. Analysts really like the SQL feature, so they have a notebook where they can, query a massive data lake, save their queries. And then for application developers, Spark streaming is just one of 3 ways, since you have Akka streams, Kafka streams, and Spark streams, one of 3 places you can send information as it changes. Usually it's probably going to be a combination of Kafka streams and Akka streams for apps to react on the data. If there's anything heavy that needs to occur, it'd probably almost certainly be in Akka streams, I think. So the evolution, most of us have worked with all of these, and seeing even older options. So you have JMS, AMQP, Kafka. It's just kind of a natural evolution. Why would anybody use Rabbit nowadays? Unless you had to. Streaming platforms. Kafka, that's one of its intended uses, to be very fast. It's a fancy commit log. They can process messages when they're provided through the streaming model, fault tolerant, pub sub capabilities, all the usual stuff. So common use cases, data pipelines, source and destination, actions, transformations. There's, schema registry with Avro in there. Bunch of MVs so you can track what the cluster is doing. And common use cases, sending metrics or weblog data. That's what we use at Cox. A bunch of our websites, like Kelley Blue Book, sends every click through Kafka. So it's literally billions of messages a month. So we have a pretty large Kafka cluster that's processing that. And again, it's a commit log. So you can create a topic, publish events to it, and each consumer is responsible for his offset. So if consumer A is ahead of consumer B, that's fine. He's just reading in an offset. And everything's ordered based on when the events were received. Clients can, push stuff asynchronously or synchronously. Synchronously will guarantee the order more reliably. So it's just a performance comparison here, and I don't know what the hardware was on here, but what's interesting to me is just the difference in performance between the different components. This is about a year old, but I don't think there are any surprises here. I was surprised Mongo was as slow as it was, but I guess it doesn't web scale anymore. Kafka, some of the Kafka APIs, these should be familiar to everybody. So you have the produce and the consumer API, same thing as JMS. You know, the main simplification with Kafka, you don't have topics or queues. It's you just have a topic, and you can have a consumer group, and that's how consumer A is distinguished from consumer B when pulling the offsets. Because if two apps share a consumer group and they're both pulling off a topic, then they'll steal messages from each other. So that's one of the problems that people run into. But other than that, it's easy. Streaming API, stream processing. You can do some interesting things, correlate streams, aggregate streams, do event-driven activities, that kind of stuff. So like some of the stuff, if you ever used Esper or the AD engines of the past, you know, similar windowing type functions there. And then the connector API is just a way to wire in different producers, consumers more directly to the Kafka cluster. So you know, think of it as like a purpose-built integration. So why use it? I don't know. I don't even know why I even asked that question. It's kind of obvious to me. Log forwarders, you know, Scribe or Flume, those still have a place in enterprise. And you know, if you're just pushing data, like a massive amount of data, not really doing much with it, and don't have any logic that would slow it down, then yeah, those are great. That's, in fact, you know, if you're dealing with weblogs or pushing stuff to a Splunk, you really have to do it that way to get the performance and to stay real time. But if you have program units that need to act on the data or do anything CPU intensive or anything that could be CPU intensive, then maybe that's where other technologies make more sense. Supports a variety of languages and more in the future. It has an extremely robust ecosystem, so I could fill up 3 slides with all the components that are in Kafka, and most of you already know what those are anyway, so I won't waste your time with it. So Spark, what's Spark? According to their definition, a fast and general engine for large-scale data processing. Basically, it's, hey, I don't like Hadoop. This is better than MapReduce. You know, it's keeps your analysts happy. So people are running Tableau or whatever. You don't have, you know, obvious difference. You're not doing MapReduce. You don't have the mapper and the disk and the reducer and the shuffling and spilling the disk in different steps and all that kind of stuff. But Hadoop is great for if you have petabytes and petabytes. It might be the most cost-effective solution if people don't need their data in real time. And you could create curated data sets, you know, and deliver them later on. So there'll always be a role for this. But for Spark, you know, usually people want immediate answers. You could have an API conceivably that could hit this through Spark code to run some kind of interactive data query. And if the data is in memory, it's 100 times faster, 10 times faster on disk. It's based on a micro-batching model, so for performance, whereas, you know, Spark might seem inferior at extremely high load to like a Storm, the micro-batching will actually allow it to scale further than Storm because it's more predictable. Some of the common tech stacks, most of this should be common. The GraphX and the mlib are interesting to me. Switching away from RDDs to data frames, newer version of Spark 2.1 or whatever it is. So different execution modes. You can do standalone. You can run it in Hadoop where it's managed by Yarn, which the downside there is that the Hadoop cluster, the Yarn will spin up a bunch of Spark containers, run the job, then they're destroyed, and whatever you've created, you lose the state. So you would have to create an always-on Spark cluster in there. Have a thrift server so that people could run Spark SQL against it, which, interestingly enough, Cloudera does not support. I think Hortonworks does, but Cloudera doesn't even today. Spark can run against data in HDFS, Cassandra, HBase, really anything. We're using it obviously a lot against HDFS and then S3. So we're actually mirroring HDFS and S3 right now, using the same, our key spaces map our URIs right now. They're not going new for long, but then Hive and a bunch of other technologies. And you can run code from different compilers. Python's popular, easy language for new people to learn. R, good for people who are in the semi-technical analyst or machine learning type data scientist mode, or else for API developers or more hardcore developers, you can Scala or Java, whatever your flavor is. And the cool thing is there's a couple different interactive shells you can use. There's IPySpark Notebook, and then Databricks has one, and there's cool CLIs or REPLs for running data. Just a quick overview of MapReduce. So I think everybody's seen this. So it's slow. This is why. There's a lot going on. This is an older slide, but the main thing here is storage. Spark runs on a lot more than that. Hadoop even has some other options to HDFS depending on the distro that's being used. But at a very simple level, this kind of explains the differences. So Spark, a clustered application, just the different components. You have a worker and Spark master. Everything starts with a Spark context. Nothing new there. Some more execution terminology, and this is older, so you have RDDs and tasks, and this is kind of getting into the process of how does Spark work internally. They use Akka for its scheduler for high availability. That's how Spark gets its high availability, is through Akka actually. So yeah, basic SQL, you can run most Hive. This is actually not true. Like there was resources I found said that you could run Hive. You can't. There's some situations where certain syntax won't work, depending on the distro. Definitely for Cloudera. And it can be a distributed query engine. So this is like one of the first federated query engines, probably. I mean, the concept has been around for a long time, like 15 years. I mean, Oracle's been able to do that, external tables for decades. And now Amazon, with Amazon Athena, you can have federated query and all this, bolt all this stuff together. So you don't have to move as much data around. And sometimes it works great if the compute can be done remotely and the result sets aren't that huge being sent back. So data frame, that's, everybody knows, that's just the core thing. As of 1.6, so is the data set. I replaced the RDD, so that's just basically the construct that is used. It's kind of like a table. So Spark streaming, which is one of the interesting things that's been added in the last few years. High throughput, high fault tolerant, processing real-time streams. It's a little bit different than Kafka in that it's micro-batched, but you get some features that you would have in an EDA engine, like the windowing and the accumulators, that kind of stuff. So with Spark, obviously you have the two different types of environment variables. You can have the accumulator or the other one that broadcasts everything to keep track of state and the share state across these processes, whereas Kafka, you don't really do that. I think there's a way to do it, but Spark is more built for that purpose. So it's more of an analytics function. So if you're building a curated data set that needs to evolve other data sets over time, then that's where Spark would make sense. That's where we use it. It's cool, you can merge inbound data with historical data in Spark, write code in any language. You can have programmatic low-level access through the D stream via streaming contracts. There's two primary metrics to watch to monitor and tune on a Spark cluster. Processing time per batch, obviously, and scheduling delay. So it's pretty simple, and it's not that different than what ops guys would be watching in a messaging cluster or anything else anyway, or even database queries. It uses Cairo for serialization. That's kind of what everything seems to be using nowadays. So then I just threw in some comparisons. Some of this information may be older, but it's, you know, Flink and Storm. Like Flink is part of the fast data platform for Lightbend, but it's a pretty interesting and cool tool as well. Used for different purposes, but you know, all these are good. Storm, you know, it's been around a long time. There's Heron, which is its replacement, supposedly backwards compatible, so I can run the Storm code. But so build a Spark application. It's super simple. You know, if you're using Scala or Java or whatever, compile a jar, and then just Spark submit it, and then that's it. Then they have GUIs that you can go to check the job status and see what's going on in the job. An interesting thing is it uses Log4j, so I don't think there's a facade in front of that, so if you want to plug in a different logger, that could be a headache, but maybe that's changed. So Akka, the next topic. This is the one that a lot of people I work with are interested in. So obviously quite a bit of use. It's interesting to me is Blizzard, like 20 million kids in there banging away, creating tons of data. And the games are running in Akka, you know, all actors and that kind of stuff to manage state. Then you have HP, the HPs of the world. So a bunch of different companies using it for different purposes. Some of them are generating, you know, a ton of data. I think I saw another slide where Pinterest was using it as well, which was interesting. So the vision of Akka, you know, concurrency, scalability, fault tolerance, obviously, basically what Erlang is, but a more modern version of it that runs on, you know, a more common JVM. So Erlang has its own JVM or VM, and the Java's been around, has a larger ecosystem. There's more tooling. Not to say one's better than the other, because Erlang's always faster, but Java's definitely got a bigger community and more tools available. Not to mention, good luck finding 100 good Erlang developers. So unless you like buy WhatsApp, because they have like 30 of them in there. Like last I heard that WhatsApp is like one server running billions of messages. They have like 35 Erlang engineers. So that's probably like the exception in the entire planet. So some of the other visions of Akka, you know, integrating back pressure, which is a big one. So it's built into the platform, so that if an actor A is working faster than actor B, then you know A is slowed down. He can't send messages, but it doesn't break the platform. It manages back pressure, and usually that's like Kafka internally. Can scale up or scale out. If you have like a Mesos or something like that, can self-manage, grow the cluster, add more members. You can program to a higher level. So no more shared state, you know, deal with state visibility, threads, locks, concurrent collections, which that isn't entirely always true because that still pops up in some Java libraries. Thread notification. So basically the thread management, deadlocks, and all that. You don't deal with that because this is process concurrency. It's not thread-based concurrency anymore. And the process is just an abstract thing that's running in a component on a server. So, you know, all the challenges, the low-level concurrency, and concurrency programs really hard. I guess they're of the most challenging types of programming. Distributed programming and concurrency are definitely up there. You know, it just becomes simple to deal with messages. You're writing actors, sending code around, and those actors can only work in very simple ways, which I'll show you in a slide. And also this very simple lightweight model, increase CPU utilization, you'll increase your throughput, reduce lag, more scalable, happier customers, faster APIs, great for a data processing engine that can scale. And it's proven, it's already in use in a whole bunch of companies, and Spark runs on top of this, and everybody's using that. It's perfect for the cloud, mainly because of its deployment model and scale model. You know, it's already fault tolerant, self-healing, adaptive load balancing, and there's different ways that can be done. Actors can, you know, become other types of actors, or if they get busy, they can become a load balancer or a bunch of different features we'll talk about in a minute. So we can build dynamically, loosely typed systems that adapt at runtime, and that can do really interesting things that are limited only by your imagination. So, you know, as I mentioned, the basic unit of the code is an actor. Yeah, that's same as Erlang. It's the mechanism to create concurrent, scalable, fault-tolerant apps atop the fabric, the Akka fabric that's running on a cluster. So it's similar to servlets or session beans. Policy decisions are separated from biz logic. You don't have like in the old world all the code mixed together like in an EJB. And actors have been around a long time. I've probably said that 10 times. And some of the Erlang-based systems have nine nines of uptime, which is phenomenal. That's like, you know, they just don't go down. So you could think of an actor like a VM in the cloud conceptually, but a very, very tiny one, or a Docker container or whatever. Maybe it's a cluster that's expanding and contracting, using non-blocking messages, but you know, the messages that are passed between actors, the delivery is guaranteed. They're highly available and fault tolerant. But the events inside, that's where, you know, stuff could maybe have to be reprocessed. So how do you use actors? You can use an actor as an alternative to a thread. So if you have like an old legacy application that's attaching to ActiveMQ and spawning a thread pool of 10 threads and processing messages, you know, doing an event-driven, message-driven approach, you just replace with an actor system and feed those messages into the Akka cluster. And it goes to the producer, it fans out to the different worker nodes and works the same way, but if there's ever a problem, you don't lose anything. You don't have a complicated system to write, all the plumbing's there for you. So in that sense, it's also an object instance or a component. It could be, you know, a microservice could be an actor. And as we'll talk about later on with Akka HTTP, you can actually expose these actors over the wire, you know, on a port as a service. And people would never know the difference between that and Spring Boot or Camel or whatever. Actors can be singletons. They can do stateful things. You can create an actor that's a finite state machine and actually send it messages so that the actor becomes something else during that state change process. And because of how they're addressed, you can actually have clusters of those, which is kind of interesting because if you have a state machine that, you know, like multiple steps and some of them are more complicated than others, then the actor system can automatically adjust to that and create actors of the appropriate type that handle load so it remains predictable. So, Carl, I think there's a link yet. Hewitt's, excuse me, the link on the bottom is Hewitt's definition of actors, our Erlang guy. He's pretty opinionated, but his presentations are interesting. But you know, the fundamental unit of computation that embodies an actor is, you know, processing, storage, and communication. It's really three simple things. So there's three axioms. You know, what does an actor need to do? What's the most simple way? And this guy figured this out in the 70s when people were using punch cards. So it's just phenomenal. You know, create new actors, send messages, or designate how it should handle the next message it receives, which interestingly enough includes, you know, maybe, hey, maybe actor A, maybe you change clothes and become actor B. So here are the core operations. You know, you have definition, creation, sending, becoming, and supervision. Defining is just, you know, the code to create an actor. And there's certain syntax or, you know, boilerplate code that you need to put in place. It's pretty simple. I think I put a screenshot on the next slide about that. And there's creating actors, spinning them up, how they're created, what creates them. You know, send, which is more about messaging. Become, which is where, kind of like impersonation, an actor can receive a message and say, hey, I need to become this other type of actor. Or, hey, I'm becoming very busy. You know, I have a lot of load, and I need to become a load balancer. I need to spin up a pool of actors below me, that kind of stuff. So there's a lot of cool stuff. You know, like limited by your imagination. Then supervisors, like you have actors that could supervise other actors, and that's how high availability and resilience is guaranteed. So you can create supervisors that watch other actors, and then they can even watch each other. So the define, so it's just the definition of the class. And you specify the message type that you respond to, and like on message handler, very easy. So in create, create from the actor system itself. They're very lightweight. You can get almost 3 million per gigabyte of RAM, just for the actor shells. Wow, yeah, I didn't cut and paste that very well. So there's strong encapsulation. It's like a queue. So and the interesting thing is, with an actor system, is there's a hierarchy. So name resolution and how you access the actors, it's like a file system. So it might even look like HDFS to people who come from the Hadoop world. Send, so that's just how you send a message to an actor. You can configure that, async and unblocking. There's a lot of features in each of these, so I'm really simplifying it. Everything's reactive. An actor is generally passivated until it receives a message, and then it'll awaken and do stuff, and eventually passivate again. So, and Jonas Poner likes to refer to messages as energy, like messages as power. So they're thrown around in the system, and they cause the system to wake up and become hot and do things. So from a physics standpoint, it's kind of interesting, like entropy in a way. So everything is async and lockless. So that's because you're not sharing state. That's how you get the high availability. So this is one. I believe this is one server, or is a 4 or 8 way or whatever. But yeah, it's scaled out to 50 million messages a second. Maybe it's just saying hi or piping to dev null, but the point is the engine is extremely fast and scalable. So for data processing backbone, this is good luck doing anything like in any other language, like in a reliable way, other than maybe Erlang would be a little bit higher than this, but not by much. So this is an example of the defining. So, and then, well, actually after it's defined, so this is remote deployment. So this looks a lot like play. People have worked with play in the past. So it's literally that simple. So to deploy an actor of the actor system. Become, that's where you can redefine an actor's behavior, change its clothes. It's triggered by the receipt of a message. How that occurs, that's a good thing to look up on. So it will not react differently to messages it receives. It still respond to the messages that it's typed to respond to. You can actually stack behaviors on an actor, which is kind of interesting. So an actor could become a stack. So you could, if it has a state machine, it can push and pop its way up the state machine, which is kind of interesting. And then I'm sure there are a lot of other ways to abuse it too. But for like graph problems or whatever, or typing or polymorphic behaviors or whatever they need to be, that'd be an interesting way to solve it. So when an object changes its type, it's not really limited. It can change its interface, its protocol, and its implementation. So literally becomes something else, like Terminator 3. So why use the become operator? A busy actor can become an actor pool or a router. You can implement a finite state machine. Graceful degradation could create a pool of empty workers that would become something in the future, just to warm them up. Again, endless uses for that very useful feature. Failure management. So this is just comparing failure management in Akka versus Java. So I think everybody's seen all the other languages, all the try-catch blocks, and even some of the latest syntactic sugar in Java. It's mixed in with all your business logic and code. And Scala's maybe a little better, but it's still there. So with Akka, you don't really deal with exceptions explicitly. There's There's a single-threaded control in Java, and if that blows up, you're completely screwed. You can't get the error out. The only option is explicit error handling. Sometimes pushing the error down to the client will have to figure out if something goes wrong because the code may not be reliable or the framework may not be reliable. So you end up with a lot of defensive code. Supervise operation. So you can have one actor A manage another actor and help out with his failures or personal issues. Can let actors monitor each other. So you could have the supervisor providing metrics or maybe coordinating watching loads, or actors themselves could do it with the supervisor and become something else. But anyway, it's a neater separation of processing from error handling because the errors are less obstructive. So the Akka streaming piece, which is interesting, it's completely decoupled from the reactive streams interfaces, and that's just the standard that's been agreed to on the interface in the industry. So that way, Akka's implementation kind of works like an SPI. You can plug it in. So theoretically, you could swap it out with what's in JDK 9, assuming they don't deviate from the standard or anything else. Just defines how to pass stream data between message streams and that kind of stuff. And all the features are expected to be explicit in the API. Principles of composing stuff, combining, modeling the domain in a distributed stream environment. And again, JDK 9 calls them the Flow API for some reason. Based on immutable building blocks, blueprints enabled for libraries. So you have some concepts that, in the event thing world have been around for a while. You have a sink, a source, flow. The biddy flow is unique to Akka from what I've seen. So it's doing stuff with multiple streams. Graph, that's working with shaped objects or graph structures. Built-in back pressure as well. So it's kind of the same features as Akka. You get that here. And the important distinction is the difference between an error and a failure. So an error is accessible within a stream as a data element, but a failure is when a stream is collapsed itself. And that's where the high availability piece of Akka and actors and guaranteeing messages flowing comes into play. So if a stream collapses, it should be isolated to a certain region of the stream topology so that then the system can recover from it. And some of the events that have been generated may have been lost, but they can be reconstituted. Okay, Akka HTTP. So this is built on top of Akka streams. It's newer. Alternative to play. We're using this internally. So it's just basically bind your actor to a port and that's it. There's a little bit more to configuring it, but you set up a route. Back pressure handling is interesting. So the actor will stop consuming from the network. So if something floods it, it'll eventually get an acknowledgement back. It'll stop. Some rules about this, is that Akka HTTP's libraries should provide the users with reusable pieces, expose factories that return graphs, certain common things that exist in other libraries. Avoid destruction of the composability of the actors underneath. So basically follow the contracts that are established for the other APIs. Alpaca is part of Akka streams. So like anybody wants a good open source project to contribute to, this is a great one because there are only several components created now. That Campbell has a couple hundred components. They want all the same functionality in Alpaca so that an Akka stream can have all the benefits of a camel, like wiring in to send an email. They already have connectors to Mongo and Cassandra and Esther and some other stuff. But it's an interesting alternative to Apache Camel so that, working within an actor model, you don't have the overhead of an Apache Camel framework and everything that it does. Community driven, you know, when I went to the Reactive Summit, that's when they kind of unveiled it, and they begged people to join the project and wrote a call to arms and put it on their first tag and all this kind of stuff. So they're pretty serious about it, but I think this is a promising library. They'll probably get, parts of it are actually folded into the Akka library as well. So just briefly, I didn't have time to flesh all of this out, so I'm just going to talk about the dark side of the data lake and kind of what we need to govern it. Now that we've spent a lot of time going through different technologies and explaining reactive principles that would help us get data to a data lake, or eventually something is done with it, whether it's just an application data store or, you know, curated analytics resources. So yeah, I'm going to expand this. So this is where the data ends up, and a lot of companies just treat their Hadoop cluster like a data vacuum. Hey, let's put it in the cluster, we'll use it later on, which is great. More data that's there. One of the intents of the data lake is to remove siloing of data, to theoretically drive adoption and sharing of information. So it's you know, it's a massive repo built on top of commodity hardware. The data is not really stored in a way that's optimized for data analysis, and maybe that's more of a problem with Hive, but since, you know, there's no governance on the structure of the data or how the data is composed or even its formatting, you know, that affects the access path to data, so that's actually important, especially large data lakes. So the data lake will retain attributes of the data that's sent to it. Garbage in, garbage out. This is a great read right here. So there's a bunch of articles like it, but it's about, you know, some of the pitfalls, so I've summarized some of those. So the goals of the data lake, you know, to drive increased information sharing usage by reducing costs through consolidation of silos. Does it really work? I think some companies are seeing, yeah, it works, but, you know, we're having trouble getting certain groups to adopt it, or maybe we thought it could be used on an application database, but, you know, they're still going to need their NoSQL data store or maybe their relational database. These other techs aren't going away. So, but this has a place in the whole plan of things. So the question of deriving value from data still falls in the hands of the business in a data lake, because, you know, if there's no governance and there aren't many tools that provide a good data catalog and way of keeping track of lineage and who found value in what data or combining what data sets, there's a lot of context that is specific to where the data came from that maybe their analysts only know. So how to share that? And there really isn't a tool that does that well right now. So the dark side of the data lake. So we have many companies tend to vacuum data in and use it later. I mean, great, you need a lot of information to have a data lake. Many companies use overlapping tools within the same ecosystem, and they don't interoperate. And what I mean by this is you might have multiple ETL tools. You might have multiple data lineage tools. Now, from the operations perspective, keeping track of all the jobs running, like if you're using Azkaban, a Control-M, Quartz, all these different jobs, how do you keep track of what's going on in the data lake and what information's there? And even who's using it? And not even to mention the entitlement model or tenancy, like how to isolate all that. So all this data is just ending up in the data lake, and maybe some people are using like the Sentries of the world or, you know, the Unix style permissions, but having a meta model to actually do that through metadata instead of admins poking around and having to hire dozens of people and having lots of process that bogs down the company, that's a challenge, I think. So data lakes largely, you know, in pure form ignore like how and who uses data and how it's governed, unless you have simple ACLs to control that, and that's about it. So does this sound 10 minutes? All right, I'm almost done. I'll actually probably hit that right on. So the data lake solves the old problem of siloing data. Great, so it's now commingled. There's some new options. There's some pushbacks. So you have federated query Athena, so which maybe bypasses some of the need to use the data lake to combine or share data assets. You know, you have an inability to measure data quality, so that's a huge one for us, that we pull in all this information. How do we measure data quality? What is data quality for what's coming into the system? So we accept data without any governance or oversight. It's just ETL'd into the cluster. We set up a feed, it's loaded. We don't know if it's good or not, what's in the fields, or if they have a date column, if that information starts getting mangled. Somebody downstream tries to create a curated asset and they can't. You know, I think the whole concept of tenancy is probably the most important, because it all kinds of starts with that. You have the concept of a data owner and data lineage and entitlements and granting access, which sounds like a lot of complicated process, but programmatically, if there were a metadata catalog that managed all of this and was a partner in how data flows into the data lake, then all of this governance could be enforced and it couldn't be bypassed. And one of the ways I think of doing, I'm working on this now, is that like just storing data in human readable format in S3 buckets or HDFS, that's what it allows people to bypass the convention. So they can look at the URI and figure out, hey, it came from this place, and here's the owner, and here's the name of the data set, and then I know somebody over there, call them up, and then all the due diligence in the world about this won't work. But if the information is stored in a raw format in a data lake in a non-human readable format, a machine readable format, maybe just hex codes, not only will it eliminate the possibility of somebody of going in there and hacking and getting at data, they would have to go through the tooling that governs the data lake. They would have to use a tenancy model. So if they wanted to find out a data set, they could even have different aliases, so that you could, you know, if I want to find data about a certain topic, go through this tool, find it, it will help map it, and then that tool would provide a way of creating a curated asset that's in a human readable representation. So, and this becomes actually very important in S3 because of how it does its bucketing and the hashing. So if you have like a long URI and the first, you know, 20 or 50 characters are the same, it might end up in a bucket and you get a hotspot S3. So, and then security and access control and all that kind of stuff. But I'm kind of treating all data like it's important, like you have regulatory controls. So anyway, more to come. I have to tighten up some of this presentation and add some more interesting content and more diagrams. So the version at DevNexus will probably be a little more concise and interesting and visual. And then try to tie together more of the technology in the data lake as far as how it actually would work, especially like an end solution. How do you make this work programmatically? And there's some software products out there do it, but there really isn't a comprehensive one right now, which is why so many companies are facing the same issues. But as far as creating a streaming fast data platform, yeah, that's the easy part. So that's it. So thanks for your time. So any questions? So, all right. Oh, I'm sorry. I have new glasses, so I can't see.
What are some drawbacks of Akka?
I think finding people that understand it right now. It seems like, well, my experience anyway is like talking about reactive programming, and when you bring up manifestos, and it scares management, so they think, oh no, this is going to be like Agile times 100, and it's going to be disruptive to my organization. So I think finding the right use case where it works. Some of its more useful features are still experimental, like the HTTP feature. So there is some complexity there. And managing an Akka cluster is not trivial by any means, especially being able to debug it, and there are some technical issues that can occur. But I think over time, the tooling, like the mesospheres or the terraforms of the world, being able to quickly and easily and reliably deploy a cluster and have confidence in it are improving. Like older versions were they did flake out. They had the goals of Erlang, but the implementation maybe wasn't quite there yet. I think now, given as adoption increases, a whole bunch of big companies are moving to Akka-based systems. Like there's the big white paper about PayPal switching their entire API to an Akka cluster. So they supposedly replaced, I think it was about 100 VMs, load balancer or whatever, running microservices with about 8 Akka nodes running in a cluster. And they satisfied the same load more reliably. So I think finding the right engineers is probably the answer I would give, and then over time, that information I think is just going to sink into the engineering community. So.
In usual web applications, we have to deal with transaction management. In this Akka, how can I manage transactions? It says that you have to think of non-blocking, and it says you have to basically pass the events and messages. But if I write a web application using Akka HTTP, at some point of time I will have to do transaction management. I cannot run away with transaction management. So how do I deal with transaction management when I'm using Akka?
That's a good question. I'll add a slide to that. I think their Saga pattern answers that, so the ability to roll back and forward. How that works with Akka HTTP is interesting. I actually haven't thought of that. I know with actors, you can use state machines and all that kind of stuff. But if you're dealing with a stateless protocol, it's a little bit different. So
whenever I do one database call, that would be a blocking call. And Akka says when you do database call, it's a blocking call. So just make it non-blocking, use promise or use feature, and try to make it non-blocking. The moment I make it non-blocking, I lose my transaction.
Yeah. So then, for that would be a good feature. I know Alpaca has an RDBMS component, which probably offers the ability to control synchronous behaviors like that. So that's kind of how I envision it. They envision the streaming is just, streaming functions, windowing, and that kind of stuff. And when those streams connect to different things like databases or queuing systems or sending emails or sending SNS, then that would be like a component, like a camel type component that would offer specific functionality for the subsystem. So I imagine that's where they would solve it eventually. And then the question of a transaction would probably need to be bounded by the scope of the actor's life or the state machine it's operating within. So that's, that'd be a good answer, like where is it complex and hard to use.
On one of the slides you had Akka and Kafka all messaging each other, and do they complement each other, or can you just use one component? I'm sure the answer is always maybe, and it depends, but how do they, like things like Akka and Kafka, kind of work together and complement each other?
So I think as a streaming, like a messaging platform just for managing messages and a vehicle for replay, high availability, Kafka is great at that, or connecting, Kafka Connect, and there's a bunch of other Kafka libraries too. For actually doing data processing, in a way, in complex ways that can scale robustly, that maybe have state machines underneath and all kinds of stuff in a predictable manner. That's where I think the Akka cluster, because yeah, you could do almost everything just with handlers off Kafka if you wanted to. So what makes sense to use an Akka cluster, maybe to use Akka streams. And then, you know, with Kafka, you can't expose a message as an API or an actor as an API, so that'd be one other important difference. And then Akka HTTP is just one option. You can use play for that as well, which interacts with the actor subsystem directly, but it's kind of nice to cut that out and have that option of you could run data, you could still process in Kafka, send it through a messaging system or an actor-based system, and you know, if you wanted to expose APIs as well as part of that community, they could share the actors as well. So like the composable building blocks that would be available. So you could have, you could use Akka within Kafka as well. So I think Kafka would be the obvious starting point, I think. Yeah, I think for us, we have our retention logs are a couple of weeks or something like that. It's like many billions of records. So depends on the topic. All right. Thanks.